Okay, so let's suppose we have x of t being the time deviations between two clocks. So you have an x of t variation, and this probably is not far different from what flicker noise would actually look like in terms of the time deviations from a quartz clock or between two clocks. And back at that time, the best way to measure frequency was using what's called the heterodyne technique, or the beat frequency technique. So you'd have frequency 1, frequency 2 going into a Schottky diode root mixer, come through a low-pass filter to get the difference frequency, the beat frequency, and this gave you huge leverage. The clocks were so good that that beat frequency would give you a huge, like a factor of 1 million to 10 million ability to measure the instability of these clocks. So this beat frequency would come into a frequency counter, and you would arm the counter, and then you would sample over so many cycles of the beat frequency, and then for some sample time tau, and then the counter would lock that value and print it out, and then you would have to wait a cycle to start the next measurement. So you had dead time between this measurement and the next measurement, and you can show that has serious consequences in metrology. So anyway, so then you take the next tau interval, set of zero crossings to measure the beat frequency over the next tau interval, and so your measurement period was capital T from the beginning of this one to the beginning of that one. And so you have dead time equal to capital T minus tau between each one of these measurements. And so you would be losing data, and it turns out we were able to show later that that has serious consequences to the statistics. So anyway, this is how we took the data. So you have a set of measurements going up to, say, n data points for some data run that you had measured the quartz oscillators against NBS2's quartz oscillator, which was tied to the Ramsey resonance or frequency determination. And so basically my thesis asked the question, what happens to the classical variance for n samples as a function of t, the data period, tau, the sampling interval, and the measurement bandwidth. And you can write that equation in general terms, in terms of x, in terms of the classical variance as thus stated. And
x is the phase?
Yeah, x is actually the time error of the clock. You can write it, x of t can be written as the phase divided by 2 pi nu 0.
Okay.
So if you look at the phase relationship, these are just tied together with the constant frequency of the clock. So this is the time error, and the interesting, you can also write the integral at x of t is equal to the integral 0 to t of y of t prime dt prime. So x is the integral of the frequency variations, these fractional, or y is equal to the actual frequency coming out minus nu 0 divided by nu 0, so it's a fractional. So when the frequency is right on, y is 0, and the deviations are measured in y as the frequency varies with time. So anyway, what I was able to show, thanks to Jim's help and Lighthill's book, that the dependence of, if we set n constant and the ratio of t over tau constant, which we call r, if we set those constant, then we get a dependence of the classical variance going as tau to the mu. And if we have a spectral density Sy going as f to the alpha, from Lighthill's page 43, we were able to do the transform relationship for general noise processes, showing that alpha is equal to minus mu minus 1. So it's a very elegant, what we call superfast Fourier transform as you take the time domain. And the thing that dropped out of my thesis, which shows the elegance of the two-sample variance, is that if n equals 2 and t equals tau, then you get the two-sample variance with no dead time. But it was some years later that we developed the techniques on using the dual mixture time difference and Jim's chronograph, how to do this elegantly so that we got rid of the dead time, and the finesse of measuring frequency stability improved dramatically as a result.
Mm-hmm. The elegance.